In this video, we're going to look at parallel and orthogonal planes. Our normal vectors are going to become very useful for us when we work with identifying parallel and orthogonal planes. And this has to do with some key characteristics of parallel and normal vectors. Vectors that are parallel have the same orientation, even if they have different locations in space. But normal vectors that are perpendicular will have a cross product of 0. These are the ideas we'll use with our normal vectors to determine whether two planes are parallel or orthogonal. Two distinct planes will be parallel if their respective normal vectors are parallel. This just means I'm looking for normal vectors that are scalar multiples of each other. Two distinct planes will be orthogonal if their respective normal vectors are orthogonal, which means I'm going to look for a dot product of the normal vectors that's equal to 0. Here's an example. If I'm given the equations for planes where the plane Q has the equation x plus y minus z is equal to 0, the plane R has the equation y plus z is equal to 0, the plane S has the equation x minus y is equal to 0, and the plane T has the equation x plus y plus z is equal to 0, I want to determine which pairs of planes are parallel, orthogonal, or identical. The first thing I want to do is find the normal vector for each of my planes. The vector normal to my plane Q has the components 1, 1, negative 1. The vector normal to the plane R has the components 0, 1, 1. The vector normal to the plane S has the components 1, negative 1, 0. And the vector normal to the plane T has the components 1, 1, 1. I'm going to look for parallel vectors that have the same scalar ratio for each pair of components. If that scalar ratio is identically equal to 1 for each component, I know that my planes will be identical. If the ratios are equal but not equal to 1, I'll know that they're parallel. So comparing the normal vector for plane R with the normal vector for plane Q, my component ratios are 1 over 1, 0 over 1, and 1 over negative 1. These are not equal ratios, so that my vectors are not parallel and they won't be identical either. The normal vector with respect to R and the normal vector with respect to T have the component ratios 0 over 1, 1 over 1, and 1 over 1. In this case, the two planes are not parallel and they are not identical. The normal vector with respect to R and the normal vector with respect to S have the component ratios 0 over 1, 1 over negative 1, and 1 over 0. I'm not too concerned with the undefined ratio because clearly it's not going to be equal to a finite ratio. This means my two planes are not parallel and they are not identical. The normal vector related to Q and the normal vector related to T have the component ratios 1 over 1, 1 over 1, and negative 1 over 1. These are not parallel and they're not identical. The normal vector with respect to S and the normal vector with respect to Q have the ratios 1 over 1, negative 1 over 1, and 0 over negative 1. Again, these are not parallel and they're not identical. The final pair that I need to check will compare the normal vector with respect to S and the normal vector with respect to T. The component ratios are 1 over 1, negative 1 over 1, and 0 over 1. Again, the two planes are not parallel and not identical. This means that none of my normal vectors is a scalar multiple of any other normal vector, so there are no two pairs of planes that are parallel or identical. Now I want to determine if any two pairs of planes are perpendicular. I'm going to use the normal vectors with their components, and I want to find any pairs of vectors that have a dot product equal to 0. N sub q dotted with n sub r gives me 0 plus 1 minus 1. A dot product of 0 tells me that my two planes q and r will be perpendicular. N sub q dotted with n sub s gives me 1 minus 1 plus 0. This is equal to 0, so that my q and s planes are perpendicular. N sub q dotted with n sub t gives me 1 plus 1 minus 1. This is equal to 1. This means that my planes q and t are not perpendicular. N sub r dotted with n sub s gives me 0 minus 1 minus 0. This is equal to -1, so that planes R and S are not perpendicular. N sub r dotted with n sub t gives me 0 plus 1 plus 1, which is equal to 2. R and t are not perpendicular. N sub s dotted with n sub t gives me 1 minus 1 plus 0. This is equal to 0, so that my planes S and T are orthogonal to each other. In summary, Q is orthogonal to both R and S is orthogonal to T. The other remaining pairs of planes have non-zero dot products, so they are not orthogonal to each other. Here's another example. I want to find an equation of the plane Q that passes through the point P sub 0 with coordinates 0, 2, -2, and is parallel to the plane R with the equation 2x plus y minus z is equal to 1. As always, when I'm talking about parallel or orthogonal planes, I first need to find the normal vector. To find my vector n sub r, I simply pull the coefficients off of the variables in my equation for the r plane. N sub r has the components 2, 1, -1. And since we require q and r to be parallel, it means that my normal vector n sub q has to have the same components. So I have to have n sub q equal to the components 2, 1, -1. This is my a, b, and c, which I plug into my equation. 2 times the quantity x minus 0, plus 1 times the quantity y minus 2, minus 1 times the quantity z plus 2 is equal to 0. Or I can rewrite it in simpler terms as 2x plus y minus z is equal to 4. This is the equation of my plane Q, which passes through the given point P naught and is parallel to my plane R. Here's a third example. I want to find an equation of the line of intersection of the two planes Q given by the equation x minus y minus 2z is equal to 1 and the plane R given by the equation x plus y plus z is equal to -1. In order for the planes to intersect, I need to be sure they're not parallel before I do anything else. So I'm going to look at my normal vectors. N sub q has the components 1, -1, -2, and n sub r has the components 1, 1, 1. The normal vectors are not scalar multiples of each other, so I know that my planes are not parallel. To move forward, I have to have two pieces of information in order to get the equation for the line where the two planes cross. I have to know a point on the line of intersection, and I need a vector that points in the direction of that line. One way to approach finding a point on the line is to let one of my variables be equal to 0. I'm going to let z be 0. This means that my q plane with z equals 0 has the equation x minus y is equal to 1. My r plane with z equals 0 has the equation x plus y is equal to -1. This is a system of equations. I'm simply going to add the two equations together, which will eliminate my y variable, and it will give me 2x is equal to 0, so that x has to be equal to 0, and that y is going to be equal to -1. My point on the line of intersection, P sub naught, will have the coordinates 0, -1, 0. Now, since our line of intersection must lie in both the q and r plane, this line will be orthogonal to the normal vectors n sub q and n sub r. I'm going to construct a cross product. The cross product of n sub q and n sub r is given by the determinant of a 3 by 3 matrix with the first row populated with I hat, j hat, k hat, the second row populated with 1, -1, -2, and the third row populated with 1, 1, 1. This determinant gives me a vector with components 1, -3, and 2. Now I'm going to go back to my r of t equation format to find the equation of the line. My equation of my line, r of t, will have the format of the vector 0, -1, 0, plus t times the vector 1, -3, 2. I distribute the t and add my components, and I get a vector with the components t, -1 minus 3t, and 2t. This means that x is equal to t, y is equal to -1 minus 3t, and z is equal to 2t. So now you get to try it. Pause the video and find an equation of the line of intersection of the planes Q given by the equation x plus 2y minus z is equal to 1 and r given by the equation x plus y plus z is equal to 1. When you are ready, restart the video to check your understanding. I'm going to start by letting z equal 0. This is going to give me an equation for my plane Q of x plus 2y is equal to 1, and for my plane R, I will get x plus y is equal to 1. This is a system of equations, and I'm going to add x plus 2y equal 1 to negative x minus y is equal to negative 1. This gives me y is equal to 0, and x is equal to 1. My point on the line of intersection has the coordinates 1, 0, 0. Now I need to find the cross product of the normal vectors. N sub q crossed with n sub r is given by the determinant of a 3 by 3 matrix, with the first row populated by I hat, j hat, k hat, the second row populated by 1, 2, negative 1, and the third row populated by 1, 1, 1. This gives me a vector with the components 3, negative 2, negative 1. Using my r sub t formula for finding the equation of this line, I get r of t is given by the vector 1, 0, 0 plus t times the vector 3, negative 2, negative 1. This becomes the vector components 1 plus 3t, negative 2t, and negative t, where x is equal to 1 plus 3t, y is equal to negative 2t, and z is equal to negative t. Be sure and let me know if you have any questions about working with the normal vector to determine if planes are parallel or orthogonal.